So it's always a wonderful pleasure to be back at Stanford. And we were asked to talk about the areas that might be interesting in our work in the next 5 years. So I decided to talk about two topics, more on the first and just a little bit on the second. And of course, these aren't the actual topics. These are the sort of big picture questions that motivate the little efforts that are going to try to make some headway on them. So let me talk about point number one first. Oops. Sorry. There we go. So in fact, I was thinking about what I'd say here. I realized that around, coincidentally, around 5 years ago, back here at Stanford during Andre's 60th birthday celebration, I was talking about what would come to occupy the next 5-6 years of my life, which is, and I think, as I said in this meeting, motivated by this expectation that was articulated very well this morning, that space-time is doomed. We have to get rid of it in a more fundamental description of physics. That there's at least one angle into this problem. The most obvious angle into the problem is to attack questions involving quantum mechanics and gravity, where non-perturbative gravitational effects are important, and the doom of space-time hits you over the head. But there's another angle into the problem, which is to imagine that since space-time isn't there fundamentally, if it's not there fundamentally, then even in the limit where we send G Newton to 0, or where we ignore non-perturbative gravitational effects, there's got to be some way of talking about ordinary standard physics in a way where space-time doesn't play such a fundamental and crucial role. Very much like how in quantum mechanics the world isn't deterministic, the h-bar goes to 0 limit of quantum mechanics doesn't all of a sudden become manifestly deterministic and turn into Newton's laws. It matches on another way of talking about classical physics in terms of the principle of least action, which is deterministic, but deterministic as a derived feature, not as a fundamental fact. And so we have this strategy. We have at least another way to go, just playing with physics under our feet, which is to try to reformulate standard physics, good old-fashioned quantum field theory, in a way that eviscerates the local space-time description so much as possible. So anyway, that was the program that was mentioned 5 years ago. Just try to find a new picture. How do I go backwards? Oh, right. To try to find a new picture for what scattering amplitudes are. There's no space-time, there's no Hilbert space, there's no Lagrangians, no Hamiltonians, no path integrals, no gauge redundancies. But instead, we identify the scattering amplitudes as the answer to a different question. And by exploring the answer, we come to learn that it's local and unitary and has all the properties we expect. I should say, in order to even have a prayer for me to end in the allotted time, I'm not going to have any references in this talk. But let me just say that almost all of this work was either directly inspired by or done in collaboration with Freddie Cacciazzo. And some of the work right at the very end was done with Yaroslav Trinka in a paper that came out earlier this week. So that was 5 years ago, and in the last year, I think we're in a very special theory in planar n equals 4 super Yang-Mills. We have an answer to this question of this character. So we've found a different question to which the scattering amplitudes are the answer, and as was also nicely articulated this morning. Any such picture involving the ideas of emergent space-time is almost certain to involve new mathematical structures. It's very hard to imagine how we're going to reproduce all the physics that we know and love without space-time in a way that doesn't involve some marvelous new mathematical structures. And so, not surprisingly, we've run into lots of marvelous mathematical structures in this business. Of course, a very powerful hint, other than these highfalutin arguments that there's something like this going on, was all the amazing properties in the actual scattering amplitudes themselves that are completely concealed in the usual way of computing them using Feynman diagrams. but which become apparent after you somehow figure out how to get to the final answers. And why is it that Feynman diagrams are hiding all this magic? It's because of their deference to locality and unitarity. You make these properties manifest at the expense of other principles and other features of the answer. So I just want to tell you a little bit about what this picture is in order to put what I think might happen in the next 5 years in context. So I'm not going to be able to define these things in much detail. But the idea is that, that once you give a bunch of external data, and the external data is just given by a bunch of four-dimensional vectors z, okay, up to rescaling their points in a projective space. It doesn't matter. The external data is given by a bunch of vectors z. That's what encodes the momenta and the helicities of the particle. It depends on the number of particles n. K is a variable that counts how many of, we're talking about gluon scattering amplitudes in supersymmetric theories. K counts the number of negative helicity gluons, roughly speaking. L is the loop order. And what we found is that this amplitude can actually be thought of in a specific sense as the volume. It's a quote-unquote volume. It's a slightly more abstract notion of volume. But it's the volume of some geometric shape. We gave this geometric shape a name. It's called we called it the amplituhedron in order to indicate its connection to scattering amplitudes on the one hand and to give a picture of some kind of polyhedron out there on the other. In the course of this investigation, of this research, as I'll come to in a second, we ran into another mathematical object that quite wonderfully the mathematicians had also discovered in the last 5, 6, 7 years or so, known as the positive Grassmannian. I'll talk about it in a moment. So that's something known to the mathematicians. This is an object not yet known to the mathematicians, and I think we're going to have an enormous amount of fun with them exploring its properties. So what is it? So I'm just going to give you some impressionistic picture of what we're talking about. This entire object is just a generalization of a triangle. Okay? So it's a really natural and simple geometric object in projective space. So let's first talk about, if I give you the 3 vertices of a triangle, how would I think about the points on the inside of the triangle? Well, the points of the inside of the triangle, if you imagine that they're masses, and the masses are C1, C2, and C3, then it's just the center of mass. The center of mass of those points is obviously inside the triangle if the masses are positive. So here already we have an interesting notion of positivity being associated with the inside of a region. And in fact, if you take a triplet of numbers, C1, C2, C3, which are the masses, modulo GL1, and you say that all these masses are positive, if you scan over all the C's, you scan the inside of the triangle. So that's the idea of the inside of a triangle. We can also think of this C1, C2, C3 mod GL1 as giving me a line in a 3-dimensional space. I can generalize that to a line in an n-dimensional space that gives me a simplex, the inside of a simplex. And then I can generalize it to a k-dimensional plane in an n-dimensional space. And the space of k-planes in n dimensions is known as the Grassmannian, so that's a k-dimensional vectors rather than just numbers, n k-dimensional vectors, modulo a GLK rather than GL1. The analog of positivity is a little more interesting. We order the columns in some way, and we take any k by k minor of this matrix in that ordering, and we demand that they're all positive. Okay? So that's the positive Grassmannian, and that's just the generalization of a triangle into the Grassmannian. So that's one object. But we can generalize a triangle in another obvious way. We can think of the inside of a polygon. And the points on the inside of a polygon are exactly the same idea, except you have to make sure that the polygon is convex. That puts some positivity constraint on the external data. Once again, you have to weight them with positive numbers on the inside. So this little formula, y is c plus z plus, scans over the inside of a polygon. And if you do the same thing to the inside of a polygon that we did to the triangle, if you generalize it into the Grassmannian, you have this simple formula that carves out a region in the space of k-dimensional planes, it turns out in k plus 4 dimensions, which are given by a positive sum over positive external data. That's the object that we call the tree amplituhedron, and its volume calculates all the tree amplitudes. You generalize the notion of a polygon, and all of a sudden you're computing tree amplitudes. Now, it's a curvy object. Okay? So it's a curvy object in a high-dimensional space. And it's possible, just like with the polygon, you can break it up into little triangles. Here you can break it up into little pieces. And that way of breaking it up into pieces is meaningful. It's a good way of thinking about breaking up the geometry. So there's one more idea, which is to hide particles. I don't have time to describe it in detail, but if you imagine starting with this big geometry, and you just literally hide particles, you try to ignore particles in some canonical way, you discover, interestingly, that you can only ignore them in pairs. And after you finish ignoring them in pairs, there's a modified kind of positivity property that, instead of just having a k-plane in k plus 4 dimensions, populates the 4-dimensional subspace dual to it with a collection of 2-dimensional planes. And this big geometry, the space of k-planes in k plus 4 dimensions, together with this collection of 2 planes in its complement, if you do the analog of the inside of the polygon in this space, that's the loop-level amplituhedron. The volume of that space calculates the scattering amplitudes at L loops. And so you see, it's pure geometry. And you discover that these important properties, like locality and unitarity, that are ultimately reflected in the singularity structure of the scattering amplitudes, and normally come about when you think in terms of Feynman diagrams with particles going on shell as they propagate through space-time. These essential properties of locality and unitarity arise here from a completely different source. They arise as a consequence of the positive geometry. Now, if you go and try to compute the amplitude, you want to figure out what these little triangles are that you can use to sort of shove in and triangulate the space. And finding the triangles is the analog of learning how to build these kind of matrices that have this interesting property. They're these big k-bion matrices with all these positive minors. On the face of it, that sounds like a somewhat challenging mathematical problem, but that's the problem that, for a variety of other reasons, our mathematician friends attacked. And they found something interesting, that just to solve this natural mathematical problem, instead of trying to directly build these big matrices, it's natural to build them by gluing together little matrices, which are positive, in a way that guarantees that the big matrix is positive. And they found that there's a natural way of doing that, associating with little pictures, little G13s and G23s that were glued together in many, many possible ways to make these big positive matrices. Remarkably, these are literally the pictures that Freddie and his friends for many years had been drawing to represent on-shell processes that compute scattering amplitudes. So this natural act mathematically of taking this volume and triangulating and breaking it into pieces corresponds to a very physical representation of the amplitude in terms of on-shell processes. Now, that's all for planar n equals 4 super Yang-Mills. Obviously, what we're starting to do, and I think what will occupy maybe not 5 years, but hopefully go more quickly than that, but will take some time, is to figure out how to extend this beyond this very, very simple baby toy theory. And the two obvious ways to proceed are to stick with n equals 4 and go beyond the planar limit, and to stick with planar theories and go to less supersymmetry. And planar theories with less supersymmetry are very interesting, because one of the things that we discovered is that this correspondence between amplitudes and on-shell processes is actually universal. Correspondence between geometry of the Grassmannian and on-shell processes is universal. It has nothing to do with n equals 4 super Yang-Mills. In fact, if you apply it to planar theories that are less supersymmetric, you find exactly the same structure, but you find an interesting form on the Grassmannian, one piece of which is related to the amplituhedron, and which computes amplitudes in n equals 4 super Yang-Mills in the usual way. And there's just literally another piece, and it's multiplicative in that way. When you study it, you discover that this piece, which is there in n equals 4, has everything to do with infrared singularities. This other piece, which is there when you go to less supersymmetry, has everything to do with ultraviolet singularities. And it's a beautiful geometric feature inside the Grassmannian that these two pieces don't overlap each other. So that's a Grassmannian representation of the decoupling between UV and IR. So there's a wonderful geometry sitting there ready to encode the property of ultraviolet physics. This, I think, is the deepest and most interesting problem, immediate accessible problem in this business, which is try to understand from this new point of view where the renormalization group comes from. The renormalization group is the aspect of the normal way of thinking about field theory where the usual formalism is at its absolute strongest. The off-shell ideas, Wilson's picture is at its absolute strongest. And somehow we have to be able to reproduce that from this other point of view. Something I find very striking is that the equation we're trying to reproduce that encodes the renormalization group, this Wilson-Polchinski equation, has exactly the same basic combinatorial graphical structure as what we just referred to a moment ago as encoding locality and unitarity for scattering amplitudes. So let me just end by saying we've seen a picture here where we think of the amplitudes as the volume of some nice region. So there's a nice region. We can break it up into pieces in many, many ways. Each one of these pieces also has an understanding in terms of a direct on-shell process in space-time, but the pieces by themselves have no local or unitary interpretation, while only the final results, when you put everything together, can be interpreted in a local and unitary way. And the fact that that works for n equals 4 super Yang-Mills, at least I find inspirational for the following wild, vague hope. Okay? And the wild, vague hope is that there's another way of computing boundary observables. Something that we've all gotten used to is that the only observables that make sense when we have gravity live at the boundaries. And if we just live at the boundaries, we're sort of permanently stuck with that. We know that, that if we want to describe semi-classical physics in the bulk, we have to deal with very, very strongly coupled physics on the boundary. And if we're permanently going to live on the boundary, there's nothing else we can do. But perhaps there's another way of computing the boundary observables, which is more bulk-like, or more related to bulk physics. And a variety of people have pictures like this. Banks and Fischler and friends draw pictures like this, where you imagine filling the inside of a space-time with diamonds. This strikes me as perhaps roughly like what we're seeing in n equals 4 super Yang-Mills, that this might correspond to a natural kind of triangulation of the real question. And each piece, and this is the important part, each piece will not have a precise local and unitary description. Just like it didn't in n equals 4 super Yang-Mills, the sum will be unitary, but each piece by itself won't have this interpretation. And that's the sort of thing I think many people are saying. It came up earlier today. We're probably going to have to deal with some notion of approximate quantum mechanics in the interior. And this might be a concrete way of trying to attack it. All right, so that's it for the first part. Let me just say 30 seconds for the second part. So that was the first part, IR to UV, trying to build the picture of scattering at very, very long distances by filling the inside of the space-time. The second most obvious feature of IR to UV is that we have to go from IR to UV in experimental high-energy physics. Obviously, with -2 minutes, I don't have time to really explain that whatever happens with the LHC, which we're all very excited about when it turns back on again, but whatever happens with it, whether it sees something, whether it doesn't see something, what we've learned so far is convincing enough that whatever it sees, the 50-year future of the field needs another order of magnitude step in energy, going up to a roughly 100 TeV proton-proton collider. And the US is very sadly a non-player in this endeavor, at least for now. But there are parts of the world that have some vision and ambition still, thank God. And they include Europe, where circular, 100-kilometer circular tunnels that could have E+E- and proton-proton collisions are being seriously talked about, where they're called TLAP for the E+E- version, and the Very Large Hadron Collider for the 100 TeV version. Fabiola Gianotti is involved with heading up some efforts to do serious studies on the VLHC. And China is seriously starting to get interested in doing this. In China, the machines also have a name. They're called circular electron-positron colliders, or the super proton-proton collider. And activities are starting now. The next 1 to 5 years is going to be instrumental in getting these things off the ground. And so I urge any of you who are interested to actually get involved and start doing something about it, especially if you're under 35. This is your future. And there's no one in a back room with cigars that's making sure that everything's going to work out OK. Trust me. So if it's going to happen, I think we all collectively have to start doing some serious work to make it happen. And as I said, there's serious efforts at CERN. There's a new center at Beijing that I'm involved with that's doing physics studies for future circular E+E- and proton-proton colliders. So please do get involved, get in touch with me if you're interested in seriously pursuing this endeavor. Thank you. The answer is we don't know. I mean, right now it seems very rigid. It seems very, very rigid, but it's also very, very supersymmetric. And you could view that any way you want. You could either view that as, well, so that's only going to, it's so rigid, it's only going to work for this theory. It can't possibly work for anything else. Or you could, well, the reason why I think all of us who have been staring at the data in the scattering amplitude suspect that it's not special to n equals 4 is that there's a kind of magic in the answer, sort of a character of the magic. You can express the answer in hundreds of different ways. There's miraculous identities that relate them all to each other. And ultimately, all those identities have this geometric interpretation for n equals 4 super Yang-Mills. Exactly the same things are true even in QCD, even in totally non-supersymmetric QCD, even beyond the planar limit, even in gravitational theories. The same kind of feeling that you're building the amplitude out of building blocks that can be put together in many, many different ways seems universal. And that's why we hope that, perhaps it's not literally the idea of positivity, it's not literally these structures, but something morally like this is more general. But until we do it, we don't know.
Why should we have expected or even hoped that a gauge theory would have a formulation that doesn't rely on space-time?
Well, it's not a theorem. It's not remotely a theorem. But I tried to say I tried to say what the motivation was in the beginning. That the motivation is that. That's right. Just like the world is non-deterministic because of h-bar, because of quantum mechanics. But the fact that ultimately the world is non-deterministic shows up in classical physics, even in the h-bar goes to 0 limit. It shows up in classical physics in the existence of another way of talking about classical physics that's not deterministic. That's the key point. That's the key sort of philosophical point. There's absolutely no guarantee and that's the danger of not attacking the problem directly. That the questions that are guaranteed to have something to do with the issues involved are singularities, black holes, firewalls, et cetera. Okay, so those kind of issues are the ones where these things come up obviously. But it's possible that we can get access to them in this much more hands-on, nitty-gritty way by trying to talk about space-time physics without it. And whether or not the philosophy is correct, pursuing it did lead to the discovery of this object. So, and that it's not like it was sort of sitting there with a sign saying "just come here," and it's sort of obviously sitting there. So that doesn't prove that the philosophy is right, but it was at least useful.
Nari.
Yeah, I have an answer to Andy, if I may, and which will immediately turn to a question to you. There is an example of an emergent space-time in a non-gravitational theory, which coincidentally also involves only planar graphs, i.e. n going to infinity, and that's the Eguchi-Kawai model. Right. Does this have anything to do with your emergent space-time?
No, I mean, of course, I've thought about that.
Both
but
have
not,
infinite n,
yeah.
both have
right.
Emergent space-time, both do not have gravity?
I don't know. I don't know. It doesn't. In many ways, it doesn't have the same feeling. But I don't know.
No, but it's not the same feeling because the perturbation theory in the Eguchi-Kawai model, you can show that it's identical to the perturbation theory of gauge theory of R4. Right. So that means since perturbation theory is identical.
That's why I said it doesn't have the same feeling. This is not only just another way of getting to the same perturbation theory. It's a completely different organization of the computation. So it's the same final answer, but the organization of the computation is and not only the organization is different, but these wonderful infinite dimensional symmetries that people discovered in in planar n equals 4 super Yang-Mills, conformal invariance, dual conformal invariance, the infinite dimensional Yangian symmetry of the theory. That's something that's just plain impossible to see in one local formulation or another local formulation. The locality makes it impossible to see all the symmetries at the same time. This picture has all the symmetries in it. And it has all the symmetries in it precisely because each building block doesn't care about any local description in one space-time or another. So that's what makes it feel like, it makes it feel quite different.
Sasha.
Well, of course, this is all the, what we literally know is just the planar limit, and the planar limit, there's no interesting non-perturbative corrections. So they're all, yeah. So, yes, of course. But so what I meant is that just the usual thing, that e to the minus 1 over g squared is e to the minus n over lambda tuft, and then the n goes to infinity limit. Perturbation theory is a finite radius of convergence, and that's all we're talking about here. So that's one of many things which is missing. So that there's even in the planar limit, we don't have a non-perturbative question yet to which the amplitude is the answer. We have a rather natural question at any loop order, and it's not like the question changes dramatically. You just add more and more of these two planes in the Grassmannian. But we still don't have some good generating function that groups them all together non-perturbatively.
Another point is that there's, in 2 dimensions, there's on-shelf
yes.
which follows from that answer.
Absolutely. In fact, so perhaps we could talk about it more offline. But in fact, there's in the usual two-dimensional story. Ultimately, there's a combinatorial backbone to the entire subject. Ultimately, the scattering is described by giving a certain permutation, and the picture of and the permutation. Decomposing the permutation into adjacent transpositions gives us various ways of describing the two-dimensional scattering process. There's an analog combinatorial backbone to the entire subject of the positive Grassmannian that's just a big generalization of that Yang-Baxter type story. And the Yang-Baxter story is actually a special case of it. And in fact, all the theories that we know that descend from n equals 4 nicely, or not descend, but are clearly related to it, n equals 4 in 4 dimensions, ABJM theory in 3 dimensions, and Yang-Baxter-like integrable theories in 2 dimensions share, can be thought of as arising from the same underlying combinatorial structure.
One more question from Shamit, or comment.
So maybe I haven't heard enough about the subject. There are other cases, especially in highly supersymmetric physics, where we know that geometric objects that otherwise wouldn't have obviously been part of the normal way of thinking about the theory appear and encode answers to questions. But it would be an overstatement in those cases to say that there's a reformulation of the theory based on the geometric object that encodes the answer. For instance, there are curves that solve the Coulomb branch of n equals 2 gauge theory, right. But the questions are really phrased in the original picture.
Right.
So you told us here about a geometric object, and if you ask the right question about volumes, that I'm not sure how you stumbled across, it will answer questions about space-time scattering. Right. Do you have a theory that would be most naturally formulated in terms of the new geometric object, where the questions would be generated internally, and where it really looks different than these other cases I brought up, where there's just an auxiliary geometric object?
Well, for one thing, this is answering the question of every scattering amplitude in the theory, not this or that specific BPS things. This is not a case that has anything to do with the. Yeah. Anyway, so it's you ask for all the scattering amplitudes in the theory, and it's the answer to this geometric question. Now, if you get into this, if you get into the algebraic geometry of this world, asking the question about this form, which is the volume, is essentially the only thing you can talk about, which depends on the external data in a canonical way. But I think maybe your broader question is what we even mean by theory in this kind of context. And I think that's also was very nicely articulated by Michael earlier today. Part of the point of having something like emergent space-time is it's not going to have a standard set of physical words associated with it. And that doesn't bother me so much right now. I'd rather start getting into a world where we're playing with objects that are doing the right thing and hopefully eventually figure out how to put the right words around them. But it's not, but let me say, it's not like there's 10,000 things you can do with this object and there's one of them that turns into the amplitude. In fact, I don't know anything else you can do with it that there's just a geometry, and then there's something you can do that actually depends on external data. That thing you do that depends on external data computes scattering amplitudes. Okay,
okay, let's move on.
Thank you.
Thank you.